Hello, I'm Robin Anderson, the material specialist within HBM Encode. I'm going to give you a brief overview of our perspective on material selection with a particular eye on fatigue performance. To do this, I'm going to follow a rough agenda of this sort. Give you an overview on the materials in general, go on to look at our old friend, the periodic table, look at microstructure, and then go on to alloy chemistry and manufacturing process and modifying the fatigue performance of metals. I don't believe I can put it better than this. It's a gentleman called Dr. David Jones of the University of Cambridge who said it this way. Very, very succinct. Without it, nothing can be done, nothing can be made. I also put it another way because there are so many things involved in being a materials engineer or a metallurgist that it's quite simple to look at it in terms of a triangle of things, and the inputs come from all of those directions. You'll notice that the word mathematics is not there, and that's because, in my opinion, it's implicit in absolutely all of this. So what range of materials do we have when we're considering selecting something for a component or whatever? It is quite enormous, and I sum it up in these little pictures, from clay on the left to glass on the right, from lithium to osmium on the metallics, the non-metals, the organic ones, from cardboard to carbon fiber reinforced epoxy. And in fact, you can see examples of aluminum and tungsten in this picture. Certainly the cardboard and the carbon fiber, and certainly some baked off clay. So what proportions of these things are used in current components and current usage? I found in the United Kingdom SMMT, the Society of Motor Manufacturers and Traders, a breakdown of materials as used on a typical motor car, typical auto. This, I have to be honest with you, as far as I can make out, this dates back to 1998, because they talk about 1998 model cars. They disassembled, and this was the outcome, although this was published in 2011. I think that on the basis of the sort of functions which these materials have, that the proportion is probably not very different even now. Although I do think that what will have happened is that the relative amount of steels and irons versus aluminium will have changed. There's very much more emphasis on the light alloys. But the relative proportions of metals to non-metals, I think, is probably much the same. If we go now to the opposite extreme, something that is highly composite dominated, I suppose is probably the correct word to use, is our friend the Boeing Dreamliner. And in this, 50% by weight is advanced composites, and then the balance is metal, and then there's other, which I presume are things like the trim, the seats, the windows, the transparencies in the front, and things of that ilk. I'm not convinced from my reading of the statistics whether this includes the engines, because they contribute a further 10 tons to the ready-to-take-off weight, and they, of course, are predominantly metallic, although the casings on them are, in fact, carbon fiber, the enclosures of them. So there you have it. There's still a lot of metallic things on the Earth that get used. And when you're setting out to select materials and so on, it's a case of where do you start. One nice way of putting this across is the technique applied by Ashby, Michael Ashby, again, University of Cambridge. And he produced these initially for creep and fracture maps, and then moved on to include other properties. This one is an example found on the web from the Do-It-Pom's website. And this shows you a range of materials from cork on the bottom left right up to tungsten carbide and silicon carbide up on the top right. And I mean, you can see at a glance from this why you don't make seals out of tungsten carbide and why you don't make structures out of silicone rubber. You might, but it might not be such a good idea. But that is an example of that. Now, having given what I can best describe as a lightning tour of the range of materials, I'm going to concentrate this afternoon on metallics and alloys, simply because we have other presentations that we give on composites and engineering polymers in particular. And in terms of this, we're thinking, because of our background, mainly in terms of the fatigue performance of these materials. I don't think I'm wrong when I say there's a plethora of alloy names and specifications faced by engineers. And so I will try and cut through a little bit of this and try and make some sense of it, and just show you that there is some background available on this. I will start with our old friend, the periodic table of the elements. Why, you might ask, will I do that? As I say, an old friend. Some of us haven't seen it since our school days, and in my case that was sufficiently long ago that elements 104 to 110 weren't on it then. And I have to warn you, there's a lot of these things are synthetic and so on since then. But I will move swiftly on. Which one of these are metallics? And you'll find, and it still amazes me when I see this, that the vast bulk of them are metallic elements. But having said that, I then ask the question, well, which ones do we use as the basis of alloys? And actually, it's not a lot of them. And of course, on that you would pick out, in particular, iron, nickel, titanium, and aluminium, and magnesium, I must add now. And to those, what do we add for alloy additions? Okay, it's a few more of them. I'm picking out from there, particularly lithium, beryllium, magnesium, and then all the elements like iodine or columbium in the US, manganese, cobalt, chromium, and nickel again. Why these metals in particular? Well, I found some nice pictures on the internet, and as I say, I've got an acknowledgement down the bottom there. Fundamentally, the metals that we started off with, and you can see this from the ages that we talk about, the Bronze Age, the Iron Age, and so on, it would have started with those that are sufficiently common in the Earth's crust, particularly those that are found as native deposits. Now, on the right of your screen, you should see a very nice picture of some copper. I haven't got a scale on that, but it's about 5 centimeters or 2 inches long, the longest, and alongside it, of course, the inevitable silver and gold, because those are the elements that are really very easy in a sense to find, although in proportion terms, tiny in amount in the Earth's crust. Okay, so we've got our copper, and we've discovered that when we get it hot, it goes soft and it doesn't form nice flint-like structures when we bash it with something else. If we take ourselves back a few years, bear in mind that this goes back about 9 millennia. So it's a very, very long period over which metallurgy has been studied in one form or another. Probably we've called it alchemy at some stage in that, or blacksmithing, or whatever. So we'll have a quick sort of undergraduate recap here. If you look at metal atoms in a metallic system, you've got them all packed together closely. There are no bonds between them. There's a cloud of electrons around them, and if you think about it like a child's ball pond, that's what a metal would be like when molten. The key message is that they're close packed and that they can move readily relative to one another. In my previous slide, I showed a 2D slice of perfect material. As you guess, life's not like that. But if you put layers of that 2D material, and you've got various options on how to stack it, this particular slide demonstrates how you can envisage, on the left there's a face-centered cubic material at the top, body-centered cubic beneath it, and on the right is a hexagonal one. And this is done quite simply by moving the relative positions of those 2D planes. The reason why I'm showing this is that all the common metallic systems that we use are based around these close-packed structures. The consequence of this, because there are regular structures at the unit cell level, is that when you get something bigger in nature, it will show this general morphology. Okay, I know I've cheated a little bit by showing you iron sulfide and lead sulfide here, but it gets the general message across that you can deduce that something's going on in there, and we need to look a little bit further. Now, what is the effect of this crystal structure on metal behavior? Well, first and foremost, they're dense. Well, I start with the example of lithium on the left, which is sort of just over half a ton a cubic meter, or in old units, half a gram per cc. And it goes up to osmium, which is over 22 tons a cubic meter. They conduct electricity, they conduct heat, and, for example, the modulus is consistent across lean alloys. And when I say lean alloy, I'm talking about something that has a few percent of something else in it. And we can vary the strength enormously by processing treatments. I needed to dig out a figure of what the theoretical strength of these things was, and the best I've come across, the most compact, is that comment by Harry Badisha on a Hatfield Memorial lecture that you could expect that you could get up to a tenth of the elastic modulus. Now, this of course doesn't happen in practice, because you would then have a potential UTS, as I say, of 20,000 megapascals, and that's not reality. As the final thing, and the thing that we capitalize on so often in life, ductile behavior is a direct consequence of that metal structure. But I've implied that you cannot get that theoretical strength, and why is this? Well, there's these little beasties called dislocations, which you may remember from courses in the past that you've heard about. And if you look at the picture I've drawn there at the top, you will see red lines describing the planes, and you will notice that one of them, the one in the middle at the top, is a half plane. Now, if you jiggle the atom that I've got the arrow pointing at a little bit to the right, then the whole plane will flip over, and that half plane will effectively have moved a half plane to the right. In other words, you can see that there's a means of moving the planes of atoms across one another. This is best described in terms of trying to move a rug across a floor. If you try and pull the thing all at once, the load is enormous, but if you put a little ruffle in it, you can move it more easily. And the other way of thinking about it is think about the passage of a worm or a millipede. They don't move all at once, they move a little bit of themselves. And so you can foresee that a metal would be able to do this. There is a classic demonstration of this, known as the bubble raft, and I've included a picture of that below. In that you can see outlined a dislocation and the effect of having different sized atoms, which you could think of as impurities or different alloying elements therein. And you can visualize it very nicely via that route. Now, these things were postulated in the 1930s because, of course, they sort of did the calculations of bond strength and things. And thought, well, you can't get that theoretical strength. Why? So they came up with a dislocation, but it took until the mid-1950s before transmission electron microscope was able to image the dislocation. What I've got here is two micrographs. The one on the left shows an as-quenched steel structure with a lot of black lines on it. And on the right is the tempered version of that, after you've basically heated it for a period and then cooled it gently. I have to point out that these images of dislocations are actually shown by the distortion in the lattice around it. It's not actually the dislocation itself, but it does show you what's going on in there. So why am I showing you a silly little picture of a couple of tubes of epoxy? Well, quite simply, I needed to demonstrate to you that a soft material, they can deform very easily, and we've all experienced the aluminium tube, in which you can deform it and get the contents out very easily. These are collapsible aluminium tubes, closed-end aluminium tubes. It's commercial purity aluminium. I think on the American Aluminium Association spec, this is AA1070. And in this condition, the yield strength is tens of megapascals rather than any more than that. You know and I know that you can squeeze it, kink it, and so on. It also shows another feature of metal behavior. When you bend it, and we always do this because when we flatten them in the wrong place, we then try and kink it back. It won't bend exactly, and usually what happens is we put a little bit of low cycle fatigue in it, and the thing splits and some of the contents leaks out. It's a pain, but that's life, and that's what metals do. Go back to a more familiar field from the engineer's point of view. What does this show up like if you deform it and measure the deformation properly, as opposed to just squeezing it and look for the kinks? On the left, I have the engineering stress-strain curve, and you can see that the region from the origin up to the letter A, we can move it, we can pull it, and it will deform up and down that, and it can return when you take the load off back to 0. But if we get past B, it will deform permanently. Very often, and this has been my own experience of test work, you cannot determine a clear yield point. It's particularly true in most metals such as aluminium, and therefore to provide consistency between the different laboratories' measures, you will take a proof strength at a certain value of strain, such as 0.2%, as I say on there. The other figure on there is one that we live by, which is the ultimate tensile strength, which in engineering terms is the maximum stress it'll experience in engineering terms. It's the point at which necking occurs, and that's the point where the material starts to slim down as the final failure location is determined in the tensile test. E then, of course, is the final failure. If you then take this in terms of the true stress and strain, you see the plot that's on the right, and that represents what is going on in the material. And I will show some pictures of this in a moment. I summarized this from our own software from Materials Manager. It shows quite clearly the effect of different moduli and different yield strengths for particular materials. On this, I've plotted an aluminium alloy, a steel, and a titanium. I've taken the liberty of using the Uniform Materials Law to provide these at a nominal similar UTS value, with that more anon. But you can see how an aluminium alloy will, of course, deform more than a titanium, and that in turn more than a steel. The effect of that change in modulus is quite clear from that. But we want to, I've been talking about soft metals largely until now, we want to turn this into something that is usable as an engineer. And in order to do that, we've got to hinder the movement of those dislocations. And here is a quick overview of some of the ways in which we do that. The obvious and classic one is the old metallurgist beating it. You cold work it, you roll it or thump it or do something to it and reduce the thickness, and you increase the population of the dislocations. And if you think in terms of that sort of network of little black lines, you can turn that by increasing that into an almost lace-like structure with the metal. And that, because they are interlocking like that, they make it very much harder for you to pass another dislocation through it. You can change the crystal structure by heat treatment, which is the classic route of quenching the steel. Heat it into the orange zone and then cool it rapidly. Depending on the steel, it'll be in oil or it'll be in water, or even in air. And this turns it into a different crystal structure, which in this case is a body-centered tetragonal, and it has then become martensite. It is very hard and very brittle. You can change the grain size, and that is usually by a thermomechanical treatment. You work it and recrystallize it. And when you've got a finer grain size, you have a harder material, it has a higher UTS, and it's very much better from a fatigue point of view. Of course, you've done terrible things to it from the creep point of view. But that's another story. And then finally, and probably most important, is you add alloying elements. Strengthen it by solid solution, or you can strengthen it by precipitation or dispersion strengthening. But we'll move on and talk more about that in a moment. Give you an example. We've talked about soft metal and hard metal. Here is one that I've pulled off from, I think it was Dewitt Pond. Is annealed and a work-hardened copper, just to show you the difference. And the difference on the lower left, you can see that the yield strength of that annealed copper is very low indeed. But once you work-harden it a bit, it gets much higher. And the other key point that I would like to show you on this, which of course has direct relevance to the fatigue performance of these materials, is that the ratio between yield strength and UTS is very different for the work-hardened and the annealed material. A demonstration of how dispersion strengthening hardens up the material If you look at the extreme left, I've got a line, an imaginary dislocation as a straight line that I'm wanting to move across those particles, which are the spherical or circular rather lumps in the material. So I'm pushing on the metal, and the line of the dislocation starts taking a convoluted appearance as it tries to form around those particles. Because of the particular size and relative hardness of those particles, it cannot do that. In order to move forward, we've got to get the line to sort of converge around the particle that I show in position 2. Position 3, it is looped right around it, increased the dislocation length, put work into the whole system, and therefore made the whole thing harder and stronger. And on the extreme right, you can see when I've done it to all of them. This is a process known as Orwell looping. What do they look like in reality? Well, here is a scanning electron micrograph of a 2000 series aluminium alloy. And in that you can see outlined there are larger particles which distinguish the grain boundary, and there are smaller particles actually within the grains. Now these are copper, aluminium particles, CuAl2, and that is the means that aluminium alloys of this type actually are hardened up. These are age hardening systems. This is an interesting one anyway, because this is how the age hardening was discovered, was serendipity, as in so much of metallurgy. It was in the Zeppelin works in I think 1911 or something. The works metallurgist made a new composition of aluminium alloy and heated it up and did all the things that he thought would harden it up, and it was still soft, and he was disappointed. So he went home for the weekend, probably had a few good steins of beer, and thought, well, that's it, I'll go in on Monday and see what I can do. But something made him check on the Monday morning that it was, was it as soft as that? And he found it had hardened up. The rest, as they say, is history. And this is the effect in engineering terms of the pure aluminium versus the duralumin. Duralumin is the classic name for a 2000 series alloy here in the United Kingdom. Again, I point out the relative levels of yield and UTS in there. Having said that, pure aluminium will yield down in below 50 MPa. You can't quite see it, it's not clear, as I alluded to when we were talking about proof strength earlier on. Finally, when we've done our tensile test, this is what the fracture surfaces look like. On the left is the pure aluminium. It's necked right down, and if it was very, very pure, even purer than that example, it would go down almost to a point. If you get a very pure face-centered cubic metal, it goes down practically to a point. What you can't see in that picture is that the elongation, the stretch in the metal as a whole, stretches way back into the plane of the slide. On the right, we have a classic cup and cone failure of the duralumin in the 2000 series alloy. And as you can see, the upper one is the cone part in the center. It's actually split halfway down, so you've got part of the cup, part of the cone. But you can see that a lot more effort has gone into breaking that material, and it's got to a certain point, and it's gone bang, as it were. I could go into the details of why ductile fracture is the way it is, but I'm not going to at this point. Right, so we've had a very rapid look at microstructure and the effect on properties. Now, to go on to alloy chemistry and manufacturing process. Nice picture of a piece of some steel being cast on the right of that picture. I will provide examples of typical additions, modifying them. Then we'll go on to a little bit on nomenclature and equivalence. Chemistry has a very big effect on the process and the ability to use that material. And I've picked inevitably here steel and aluminium, partly because, of course, they're the major alloys that get used. It's one of those lovely accidents of history that carbon steel has lower carbon in it than cast iron, basically. As I say, several percent in its cast iron. But the key point there is that you can put up to 1% of carbon in there. You will increase the hardenability, you do interesting things with it, but you'll also increase the brittleness. If you add chromium and you get past the 12% mark, you end up with stainless steel. And this is another example of serendipity. Harry Braley here in Sheffield, who got his chromium additions a little bit high, left it on the scrap heap, and I've absolutely no doubt that in those days Sheffield was a very, perhaps I should call it acidic place, but anyway, when he went back to the scrap heap, there was a load of rusty metal there, but there was one very bright and shiny piece, and the penny dropped. Sling chromium in it, and you get stainless steel. If you put nickel in there, we're talking about levels of tens of percent, you end up making it very much tougher. You can do all sorts of interesting things to it in terms of its ability for cryogenic uses. And you end up with austenitic stainless steel, which is a face-centered cubic material, which has different properties. It's non-magnetic, for example. It can be formed quite readily, and so on. And move on very quickly to cast aluminium alloys. If you add silicon to those, you increase the fluidity for the melt, and you also enable it to a greater or lesser extent to be hardened and age-hardened. If you add it up to 12%, you end up with a eutectic composition, which is the lowest melting point of the aluminium alloys in general use. But generally, you have less than that. The composition determines the alloy family, as I've said, and this is really a summary of what I alluded to in the previous slide. Give you a chance to have a quick look down it. And I also add the initials NB are used in this part of the world for niobium, which is the same as columbium in the States. I can't think of many of the elements that have different descriptions in different countries, but that's one of them. There is a quick summary. And the resulting UTS range, as I say at the bottom, is quite large. It's from 250 to 2,500 MPa, but nowhere near the theoretical strength we've referred to in an earlier slide. We come on to nomenclature. I wish, and I'm sure every engineer on the planet wishes that it was universal now, but it's not yet. But certain approaches tend to dominate, and I pick out from this the American Aluminium Association. I picked out probably the ones that we use most. The 1000 series are basically pure aluminium, varying levels of purity. 2000 series, the aluminium copper magnesium systems. 5000 series magnesium only. 6000 series magnesium and silicon. And 7000 series, which is the highest strength. I should also add there's the 8000 series, which is the aluminium lithium alloys. 2000, 7000, to a lesser extent 6000, but also 8000 are all heat-treatable alloys. Wrought steels, again, it's an American description that is frequently used. It's the SAE, and this is nice and logical in that it has one at the leading digit for plain carbon, and then you get the first two digits give you the alloying content. The final two digits give you the carbon content, so you can see at a glance, which is great. Sometimes the naming involves a figure for the properties, and in this case it's the yield in KSI, HY80 through to HY130. Then we go to the Werkstoffnummer, which is the DIN standard, and the leading digit gives you the alloy system. On here I've only put one, which is the iron-based, the steel-based ones, but you will see other digits. And if alloys get accepted, they get a proper Werkstoffnummer. And for example, 1.4509, I give the British stainless steel equivalent for the American Iron Steel Institute type 441. And then you can get now, because obviously these things extend, you can get additional digits for information on production route processing. This I describe in my notes on it as the world's favorite aluminium casting alloy. We're getting nearer. There is an ISO for it, which is aluminium silicon 7 magnesium, which gives the game away. 7% silicon, a bit of magnesium. It gives you a little bit of heat treatability. It has a Euro-num number, which is the EN. It has the US number A356. And then further down the list, you can see the German, French, Italian, and Japanese specs. Further down the list, you'll see our old friend here in the UK, which is LM25. There's a lot of history of metallurgy, and that's really why all these differences are there. But we're working away from them, and at this point I should also add these are near equivalent. There's no such thing as an exact equivalent. We like to think there is, and there's specifications that fall within other specifications. So if you buy to such and such a one, it's cleaner, nicer one. In the case of LN35, that is a classic A356 meets LN35, but vice versa is not necessarily the case because the iron content, for example, is a bit higher. Finally, modifying the fatigue performance. If we increase the UTS, we improve things in the high cycle region. If we reduce the grain size, we improve things. If we reduce the level of unwanted elements, the intermetallics or the impurities, all these sorts of things, we make life better. We can also surface engineer that material. What I've given here is very much a very brief overview of the sort of things that can be done just to help us on our way, wearing the fatigue hat. I put up my example of the copper again. This is work hardened versus annealed. And then I show you, as an example from our own database and software, what the effect of increasing the UTS is. This particular steel is SAE 4130, heat treated to two different conditions, one of which has a higher UTS than the other. And you can see at long lives that's decidedly beneficial, but of course at short lives it's not so good. Take this one step further. This again is a steel with the same composition but different heat treatments. In this case it's 1045, so it's 0.45% carbon, but a plain carbon steel. If you look at those UTS values, you will see that the 1343 megapascal UTS doesn't give you as good performance at long lives, but is very much better in the short life region. And if you end up having a structure where it gets into those sort of conditions, you really don't want to use the hard version. What does this all mean for an engineer? As I say, it's often difficult to actually find fatigue properties for your material, your particular material. I spend quite a lot of my time trying to help people find stuff that can be used. And my suggestion is always choose something similar for the first estimate. We metallurgists are a fairly sort of boring lot. From Arizona to Zambia, as I put it, the basic metallurgical solutions remain the same, and it doesn't matter what the nomenclature is. We will add silicon to make the casting alloys more fluid, or we'll add chrome to make it harder, or stainless, or whatever. So even if the numbers that appear on the screen are not the same, it's quite likely that there will be a similar alloy family that you can use. In the past, some work has been done to produce the statistics on a similar set of the steels, and this has resulted in the Uniform Materials Law, which is the classic one of trying to think up some fatigue properties from simple static properties that you have. It's something which is a last resort. It should never be used for design because it can be non-conservative, which would be disastrous. But as a first pass design, it is possible. Our advice is always, if you're going to use it for a final design, and the weight is crucial and all these sorts of things are critical, then you should measure the parameters on the actual alloy in the condition in which it has been processed. Bear in mind my comment about work hardening, for example. When it comes to casting, if you think in terms of the different casting processes, if you've got a very coarse-grained casting, you'll have a very different fatigue properties to something that is finer grained because it's been chill cast or used using a process like squeeze casting. Just to give you, to round the message home even further on the UML or Uniform Materials Law, these two lines, ignoring the legend underneath, but these two lines offer a material that has the same modulus and the same UTS. One is using the Uniform Materials Law, and the other one is a curve which was actually measured on an alloy. And you can see that the UML is actually non-conservative throughout the life range. So my key messages to leave you with are that the alloys are similar wherever you are in the world, despite the national standards. But to warn you on standards, they're very useful. in that you can specify and buy according to them. But they are always based on minimum values, so you don't actually know what it is you're getting in mechanical terms. If the alloys are lean, then you can assume textbook values are moduli. The reason I flag that up is because the modulus is a parameter that is so often taken for granted. It's not necessarily one that you should use the output from a tensile test for. There are much better methods, such as the ASTM E111, which gives you a much more consistent value of modulus. I warn about the business about fatigue properties based on the Uniform Materials Law. One of the difficulties in this is that actually fatigue properties are not that generally available. Very often companies will have tested the stuff themselves, and this is their edge, and they will keep it to themselves. In reality, there's no good foolproof way of generating fatigue properties from static data, and I cannot underline that enough. And then finally, because of the key effect of processing, the safest route is always to test the alloy exactly as used. I need to put my sources there. This is just a quick shift through it. Do It Bombs, Wikipedia, and Flickr, and the remainder of my own pictures that I've produced in there. Some obviously sourced from our own software. And to leave you with, I have some references that I've